resistance. Hopefully you learned last week about solving the work energy type problems and collisions, and when momentum is conserved, when kinetic energy is conserved. I'll do a little reviewing of that. First, let's look at this picture and then move on. Now, of course, I find this hilarious. This is why women live longer than men. If you look at the picture there, you have three men doing something that seems rather silly. So what seems silly about what they're doing there? Okay, they're putting an AC on the wall, yes, but it's not silly to put an air conditioner up. Okay, this guy here is standing on a ladder supported by air, right? And we tend to say, is the ladder really strong enough for that? First, and second, what happens if, he falls down? Why isn't he falling down? You have these two guys here. This guy's putting a force on the ladder like that. This guy's putting a force on the ladder that. This guy's putting a force, and I will just split between his feet and put it there. And what we will learn about in this chapter, the chapter on equilibrium, is about torques and how you notice the heaviest guy is the one furthest out on your left. This actually should be a safe situation, but it sure looks like an unwise thing to do to me, mostly because I don't trust the strength of the ladder itself. So this is illustrating torques, one of the things that we're learning. Now, the exam that will be a week from tomorrow will cover material through what Keith Reese taught you, and I will finish up some of that. So the stuff on equilibrium and torques will not be on the exam next week. I saw Course on the 7th afternoon, and he informed me that I must remove this problem from the homework. And I figure when Corso demands something, at least this time, I will do it. So I removed it from the assignment, but I also promised I would work through it. It turns out that this is not a difficult problem. It's a very good standard work energy type problem. And as we work through it here, because I'm going to work through it, we'll see exactly the process. Now, first things first, I have a question: why not solve this with forces and kinematic equations? There is a very simple, good reason that all but 6 of you cannot solve it with forces and kinematic equations. Anybody know why you can't do it that way? It involves calculus is correct. The force of the spring changes as you stretch it more and less, which means that the net force acting on that mass is going to be changing based on position. If the net force is changing, then Newton's second law tells us the acceleration is the net force divided by mass, so it has a changing acceleration. And unless you know calculus, that's the end. Changing the acceleration, you have no tools to solve. Now, the ones that have calculus in class, yes, they could go through and do an ugly problem with forces. But we have two ways of solving our dynamic problems: the force method and the work energy. And this problem with work energy turns out to be simple. So really hard with the force method, really simple with work energy. Oftentimes that's going to be the case. Oftentimes you can solve it both ways, but it'll be simpler with the work energy approach. Now, Lauren asked me a question yesterday, and the one she asked me, you saw my reply, right?
Yes.
Huh?
I didn't do the test read.
Well, okay. I worked out both this work energy problem and using kinematic equations. That one was easier with kinematic equations. So you kind of have to judge the situation. None of the steps involved for solving a problem like this. Right? When it comes to the test, a week from tomorrow, you're going to have something that is similar, not, a mass on an incline to the spring, but something that's going to require work energy, and you need to know the steps to do it. So let's go through those. What's the first step you would do on the exam? You what? Okay. First step, she says, is a free body diagram. Now I'm going to write this down. And then I'll tell you why actually that's not the first step I would do. It doesn't hurt, but what was the purpose of making a free body diagram? Show all the forces so you can apply Newton's second law. I've determined that I can't solve this with forces in Newton's second law. So since I can't solve it with forces in Newton's second law, the free body diagram is not as important to me. But what is important is going to be the work and energy. And you have two types of energy. What are the two types of energy, fundamental type of energy you talk about in class? Potential and kinetic. Kinetic energy is ability to do work because it's moving. 1/2 mv squared. It's a scalar, it doesn't have a direction. That's why I like work energy when I can do it, because it has no direction issues. And then we have potential energy. What's potential energy associated with? I heard an answer from over here somewhere. Okay, gravitational potential energy is associated with height. Potential energy in general is associated with what we call a conservative force. Conservative forces, there's lots of different definitions for them. If you have something that the force will, if you do work against that force, it will return the same exact amount of energy to you, that's a conservative force. Another way of identifying conservative forces are if the work done is path independent. So I will use an example of Corso's phone. If I want to move Corso's phone from here to here, I can push it like this, and I did a certain amount of work. I had a force I applied to it, a distance it traveled, but I could have also taken a different path. I could have gone down here, over here, over here. With the same amount of work I had to do to move from point A to point B on those two paths. The answer is no, but let me explain why. The force of kinetic friction is always going to be in what direction? What direction will the force of kinetic friction be? The direction opposing the motion. So if I was pushing it that direction, kinetic friction was pointing this way, I was pointing that way, my force then would be the same direction it moves to overcome kinetic friction. So that means I'm doing a work that is positive. Kinetic friction is doing work that's negative. No matter what direction you push it. And the work done by friction, force times distance, the kinetic friction will be constant. And so it's just the amount of work done by friction is proportional to the distance it traveled. So if I had two different distances to go from point A to point B, one the direct route, one the circuitous route, the circuitous route with a bigger distance has more work done by friction. So friction is not conservative, the work dependent on the path you chose. Anything that's conservative force has a potential energy associated with it. And you should remember the definition of potential energy is change in potential energy is equal to minus the work done by the force. I'll put a CONS because only conservative forces give you potential energy. So that's the definition of potential energy. It's defined by its change. That has some important ramifications. When I talk about the gravitational potential energy, I can choose the 0 point wherever I want because the definition for potential energy only has to do with the change between two locations. So in this problem, you see that they identified, we're going to consider a height of 0, the unstretched length of that spring. And so that's just where the 0 is, and we'll calculate our potential energy due to gravity using what Corso said due to height from that. But this is where, and the biggest reason I did take away the free body diagram, gravity is not the only conservative force acting on that mass. What's the other conservative force? Okay, She said normal. Here's a funny, incorrect statement you read all the time. Normal force can do their work. If I'm standing in an elevator and the elevator moves up, the normal force is doing work on me. If you have a stationary surface, then the normal force does no work. So you have a funny thing there. But normal force, using that normal force does no work, then it's not a conservative force, it's just a non-working force. And so in a case like this, where the surface is not moving, it's not doing any work. Okay? It's force acting, right? So that's a reasonable answer. So let's look further. Another conservative force, another one associated with potential energy. Okay, friction was a non-conservative. That is dependent on the path. And so we have to separate our conservative and our non-conservative forces. So I will make a list here. CONS, non-conservative, and I'll put another one, other. And I'll put normal in the other. Why is normal in the other? Because it's just not doing the work. So we had, for conservative, we had gravitational. I'll put gravity because it's shorter. We had friction that was non-conservative. What other forces are acting on this? We're down to one left. On this mass, what's going to be putting forces on it? We did the free body diagram. We have the spring. And the spring is another conservative force. You should basically, well, it'll be on the equation sheet. It'll tell you potential energy for a spring is equal to 1/2 kx squared. There's your hot tip. The spring is a conservative force because I give you a potential energy equation. I was going to say you should have that memorized, but it will be given to you. You should know that friction is a non-conservative force. That's really important. Also, when I was pushing on that, that was non-conservative. I can't, like weightlifting. You're, let's say you're doing a military press. You have the bar here, you lift it to here. Did I do positive or negative work on that bar? If I raised it from here to here, I did positive because the force I applied was up and the distance it moved was up. If I come back down, do I do positive or negative work on it? Negative, because my force was still up, but it came down. Did I get the energy back when it came down? No. So it's not conservative because the energy didn't return. Okay, so there are forces. We have our conservative ones. So we have free body diagram. Like I said, it doesn't hurt to do that. I'll go ahead and leave it there. And so I'll put 2 where I would have started is diagram. Draw a diagram for the situation. 3, identify energy at each state. So in this problem, I basically have 2 states, the beginning and the end. So I'm going to identify the energy in each of those 2 states. After I identify the energy in each state, I need to find work non-conservative. Let's just make separate steps here. Apply the work energy principle. And finally, solve the baby. So let's go ahead and do those steps. So step number 1 or number 2, my figure. So I'm going to have a spring, and the box is going to start, let's say here. That's a bad idea. So here's my starting condition with a spring. And I have more to add to that, but I'm going to do my end position as well here. So ending, I'm going to have Something like that for just how's it going to start, how's it going to end. I need to specify then the distances and things that we have. And so looking at what's given to us, d is the distance from the equilibrium position to how much we've compressed the spring initially. So the equilibrium position was shown up here, and d is how much it moved down to compress it. Actually, let me make sure I read this carefully. Remember, that's always the first step. Read the problem carefully. Is initially at rest, inclined plane is an angle. Blah, blah, blah. Take the initial gravitational energy to block 0. Okay, so I was wrong. I'm taking the height as 0 right here. So right here, okay, that was the wrong color. Pink will do. So going right to the center, y initial is equal to 0. So it starts with the y initial is equal to 0. The spring is compressed to the distance d. What's the speed initially here? Before I release this mass, what's the speed going to be? Gila is right. It's 0. It doesn't, well, actually, it does say it starts at rest, doesn't it? But even if it didn't, if it says you release it, you have implied it starts at a speed of 0. So that's my initial condition. My final condition can have a y final here, a v final here, and the amount it's stretched that I need to determine. It tells me that this total length is L, that it moves the distance L, right? If the spring pushes the block up the incline, what distance L in meters will the block travel before coming to the rest? So it tells me that's what L is. So if this, I started the wrong place. Just started here. There was my D. This is L. What is the distance that the spring is stretched in this final case? It moves the total distance L. It was initially compressed D. What's the final stretch distance? L minus D. So now I've drawn out my figure. That was step 2. Now identify the energies for each state. If the initial speed is 0, what's the initial kinetic energy? And if the initial height is 0, what's the initial gravitational potential energy? And if the spring is initially compressed a distance d, what's the initial spring potential energy? Potential energy for a spring is 1/2 k delta x squared, where delta x is the amount it's either stretched or compressed. So what's its initial spring potential energy? What's the equation? 1/2 k delta x squared. What is delta x initially? D. So that means it's going to be 1/2 k d squared. So those are all of my initial mechanical energy terms. Now, since I wasn't here last week, I hope he specified the word mechanical energy is different from energy. Okay, energy is something that can't be created or destroyed. When we get to thermodynamics, we will learn the first law of thermodynamics is energy can't be created or destroyed. But you can transform it from one type to another type. Some types are useful to us, some types are not. Mechanical energy is the type that's generally useful to us. So mechanical energy includes kinetic energy and potential energy that we can use. Other types of energy, thermal energy, stuff that's hot. That's not easily accessible to us. So those are our mechanical energy terms initially. Now for the final case, what's the kinetic energy final? V final is what? What's the speed at the highest point it reaches? 0. And so if the speed is 0, what's the final kinetic energy? 0. How about the potential energy due to gravity? Corso told us that it depended on the height. What's its height in the end? I call it here my final. And since work is force times distance, the work done by gravity as it goes up, force of gravity is down, the distance is up, so the work was minus mg times the distance. But since potential energy is defined as minus the work conservative, the change of potential energy is positive, so it went up to mgy final. And then we have potential energy for the spring final. What's the final potential energy for the spring? Okay, I heard Corso because he's close to me. 1/2 K times what? Well, it's delta x squared, but how much is it stretched in the final case? L minus D, point squared. Now, I do need to do something about that potential energy gravity final. I put in terms of y final, but what is y final? Y is the vertical component of its position. So if it moves the distance L up the slope, how much vertically did it move? Now, on triangle, the hypotenuse is L. We want to find this vertical side. Right, opposite side of the triangle is going to be the one with sine. So that's going to be mg times L sine of theta, where there's the angle theta. So I have identified each energy, what I called step 3 here. Step 4 is find the work non-conservative. I didn't give myself enough space. It's okay. That did not do it. I don't think it did. Nope. Nope, that didn't do it either. But I think that did screw everything up. That did. We're fine. What's going to be doing my non-conservative work? Friction. The force of friction, if it moves up the slope, what direction is the force of friction? Down the slope, the other direction. And so the direction of motion is opposite the direction of the force, which means that sine is going to be negative. So work non-conservative is equal to minus the force of friction times the distance it travels. Oh, Lordy, how do I find the force of friction? Somebody say you don't. How do I find the force of friction? Over force times mu. So the force of friction is equal to mu times force normal. What's force normal? It's like, well, there's the force normal acting on the box between the box surface and the box bottom and the surface of the plane. If we go back to the free body diagram, because now we can see, hey, there's a reason for the free body diagram. We had force normal, which is always in the normal direction. We had force gravity, which is straight down. And then we had, in this case, the force of the spring. Originally, the force of the spring was pushing up. And once it starts moving, we would have the force of kinetic friction pointing down. there's our free body diagram. I need to find how much of that normal force is in the vertical direction. How can I find that? I have to break it into components. I'm going to have, if I define my directions as, let's do it more wisely. If I do it like this, then my force of gravity is equal to, there's the same angle theta, force of gravity is equal to minus mg cosine theta in the y direction and minus mg sine theta in the x direction. And force normal is equal to force normal all in the plus y direction. What about my force of friction, force of spring? What direction are they? They're in the plus and minus which one? Okay, if I find x and y as shown here, what direction are the spring and the normal and the friction forces? They're in the x direction. So I am simply going to do some of the forces in the y direction is equal to mass times acceleration in the y direction, which is 0. Right? You can see the free body diagram that Gila said we actually have to use now. Looking at how I break down, that's going to be force normal minus mg cosine theta. Those are the two components in the y direction, equals 0. So force normal is mg cosine theta. So work non-conservative is minus mu times mg times cosine theta times L. Now, it seems like I've done a lot. It actually was all very mechanical, but I asked you lots and lots of questions. Here's what I actually moved. I asked you lots and lots of, whoops. This part here also got moved, and I tried to give myself space. Yeah, didn't work out right. Now we're to the end. We put it all together. Work non-conservative is minus mu mg cosine theta L, but that's also equal to change in kinetic energy plus change in potential energy. So I'm going to have minus mu mg cosine theta L. I'm going to put a parenthesis around the cosine theta so we don't think that L is part of the argument, is equal to kinetic energy final, 0, minus kinetic energy initial, 0. That was easy. Plus potential energy gravity final, minus potential energy gravity initial, and finally, plus potential energy the spring final, minus potential energy the spring initial. Now notice I skipped over part A. I figured probably everyone got part A. No one asked me about A. They only asked me about B. So there I have one equation, and the only thing I don't know in that equation is L. And what am I solving for? L. So we are good to go. The first thing to note here, I had students contact me saying, they use the quadratic. Don't need the quadratic to solve this. Because this last part, the only part that has the squares, if you expand out L minus D quantity squared, it's L squared plus D squared minus 2LD. But that means you're going to have a 1/2 kd squared minus 1/2 kd squared. And so when I expand this out, and because I did not give myself good spacing, I have to write over here. Okay, I didn't remember everything. Okay, so this here was expanding 1/2 k times L minus D quantity squared. And you can see that the last two terms are going to add to 0. These two terms add to 0. And what I'm left with is an L in every single term. So if I have an L in every single term, under the assumption that L is not going to be 0, that is under the assumption that it moves, what can I do? I can divide the L out. So I have now minus mu mg cosine theta equals mg sine theta plus 1/2 kl plus, notice 1/2 times 2 is just 1, so I'll drop that, kd. That's the only L. So I just rearrange and solve for L. So I will rearrange, subtract the, I believe I made a sign mistake here somewhere. Final minus initial. Well, looks right. Anybody see a sign? Oh, yes. The sign mistake is right here. This one here should have been a minus. This one here was a plus. I put the sign with the wrong one. That was a minus. Those still added out to 0. I put my signs in the wrong places. Embarrassing, but important. So the one, this here was a minus sign. So now to solve for L, I'm going to have kd minus mg sine theta minus mu mg cosine theta equals 1/2 kl, divide both sides by 1/2 k. And now I have an equation for L. So putting it in its simplest form, that's what you get when you do your work. Now, everybody had different numbers, so the result is going to be different for everyone. I know, I took a long time to solve this because I kept asking you questions, making sure that you can see the process, that I'm not, just randomly putting things up there and say, see. But in the end, what you needed to do was find the initial energies, kinetic energy, gravitational potential, and spring potential in this case. The final energies, calculate the work non-conservative, and then say work non-conservative is equal to change of kinetic energy plus change of potential energy. And so the process was very straightforward. And if you understand the process, you can do this entire problem in 10 minutes. But of course, I took 35 minutes, to do it because I wanted to make sure I explained every step. Now, any questions about how we solve this problem? Because while you won't see this problem on the test, you will have a work energy problem that requires you to go through the same types of steps. Yes? Okay, So if you look here, there's an L there, an L there, an L squared, an L, and then these two subtracted away. So every term in this equation had an L in it. So I divided everything by L. And then the only L that remained was this one. Now, why were people trying to use the quadratic? I can tell you the answer. I'm not completely an idiot. It makes sense. Because part A had to calculate the block's initial mechanical energy. And so since you already had a number for that, you didn't leave that in terms of D, which meant that you didn't subtract these two out. And then you had something that requires a quadratic. Was it wrong to do it that way? No, it was not wrong. It just was a little more difficult. So physicists are always looking for the easy way out. That's why I did it fully. Okay, let's go to our first clicker question. This one now is going on to momentum. So it's open now. In which case is momentum conserved? So you have four options here for conservation of momentum. While people are answering, just to make sure, I do not see Michaela Cohen or Trace Jensen or Jamie Stewart. Okay. And Brittany and Noah haven't answered yet. Getting logged in. And what's your status, Noah? Getting logged in. Okay. Even though I have 8 clicker questions, we're clearly not going to get to all of them, so I want to make sure Brittany has a chance to answer. There we go. Okay, so we have pretty split there. Cole, yes. Tell us what you think.
Well, I'm just guessing that in an elastic collision, things keep moving. So some of the momentum is conserved there because it's transferred to another body, whereas in inelastic collision, it would the body that's moving just stops.
Okay. Now, that's not perfectly correct, but it gives you an idea of what we've learned, right? Because I wasn't here, I didn't lecture on it, so I don't know what you've learned here. But let me back up to an easier question, hopefully an easier one that we're going to be looking at in lab tomorrow. What is an elastic collision? So for Cole.
Oh, you want me to answer it?
Yeah, what is an elastic collision?
Not entirely sure.
Okay, that's fair enough. Once again, I wasn't here, so I don't know what he said. Elastic collisions are collisions where you have kinetic energy return. A completely elastic collision, and when we say elastic collisions, we usually in our brain mean completely elastic. A completely elastic collision means that the total kinetic energy before the collision is equal to the total kinetic energy after the collision. That's what an elastic collision is. So if you have something like, let's say, you have a football player tackling another football player. If energy is absorbed by the players, then you're not going to have the same final kinetic energy. Some was absorbed, and so that's inelastic, or at least partially inelastic. But if there is no energy absorbed, then you're completely elastic. Now, as you might guess, there's no such thing truly as a completely elastic collision. If you have like a steel ball bouncing off a steel floor, it's something like 96% of kinetic energy return, which we would consider completely elastic for general physics purposes. Super balls, like you generally consider that completely elastic. But completely elastic doesn't really exist. We're going to come really close to it in the lab, though. In lab, we're going to have two cards that come and don't touch, but magnetic repulsion pushes them apart. They don't touch, so you're not going to have really any energy lost to that interaction. And so it's very close to completely elastic. Completely elastic, no loss in kinetic energy. Now, if you imagine that I am punching a punching bag, I hit that punching bag. What does the punching bag do when I hit it? Okay, it swings back. It also does something else. It collapses a little. My fist goes into it. So I was applying force, and there was a distance for the motion of the surface. That absorbed some of my kinetic energy. Where did it go? It had to go somewhere because we can't make or destroy energy. It went into deforming the stuff inside and ultimately heating the stuff up. That was kinetic energy that was lost. So that's inelastic. Completely inelastic is when two things stick together. So for general physics, we simplify these terms to completely inelastic, what is called inelastic. They stick together. Completely elastic, we'll just call elastic, and all kinetic energy is returned. So kinetic energy is conserved if it's elastic, completely elastic. So that's what those terms mean, neither of which have to do with momentum. So we need to talk about momentum. Momentum you learned is symbol P, mv. It's a vector. That's momentum. Newton's second law, here's Newton's second law in its exactly correct form. Force net is equal to dp dt. That's the exactly correct form of Newton's second law. If you don't have calculus, we write the non-calculus version. Net force is change in momentum over change in time. If I solve that for change in momentum, then the change in momentum is the net force multiplied by the time. Now we get to being able to answer the question. If momentum is conserved in physics, what does the term conserved mean? Not lost or gained. Conserved means the amount stays the same. So if momentum is conserved, what is delta P? 0. By definition, if P stays constant, delta P is 0. So momentum is conserved if delta P is 0. In that equation, you can see two situations that would make delta P equal to 0. What are the two situations, two numbers, that would make change in momentum equal to 0? Okay, if the net force is 0, then your momentum has to be conserved. What did you say? The second one is a kind of a silly one. If there's no change in time, then momentum is conserved. Well, it's silly because at an instant, momentum shouldn't be changing, but it changes from moment to moment. So now, how is that useful to us? Well, for starters, if I take this and I drop it, is the momentum of this tape going to be conserved when I drop it? No, why not? The net force on it is not 0. And so as soon as time starts running, I let go and time runs, it's going to have a change in momentum. But if I make my, okay, so this has the force on, once again, this class here doesn't exist. So the only thing that's making a force on this is gravity. Gravity from what? Earth. So if I make my system be Earth plus this, then when I drop it, the net force of the Earth plus this is 0. And so the momentum of the Earth plus this will remain constant. When I was in college, one of my friends went to a community college to take her physics, because a lot of people do not try to find teacher class. And she thought her teacher was so cute because he said, whenever you lean down to pick a flower, the Earth moves. Because of conservation momentum between that flower and the Earth, if you raise the flower, the Earth has to rebound the other direction. Of course, nobody ever notices that because momentum is mv, the mass of the flower is so minute compared to the mass of the Earth that you don't notice the motion of the Earth. You only notice the motion of the flower. Okay, so coming back to this, two conditions for momentum conserved. Either F net equals 0 or delta T equals 0. When we do collisions, like let's say it's a collision between two automobiles. Between two automobiles, you have the tires skidding on the ground, hopefully. Hopefully, somebody realized something ain't right and they're trying to slow down to avoid collision. So that means if you're just looking at your system as the two cars involved, technically the net force of the two cars is not 0 because you have that frictional force that's an external force acting on the cars. But, and you could verify this experimentally if you were an idiot. Put your hand between cars to measure the force. I suppose the force of the cars hitting each other will compare to the force of friction. This is not a hard one. The force between the cars is much bigger. The acceleration that results from the collision will be much greater than the acceleration that's resulting from braking. So the force of friction for the brakes is actually negligible compared to the force between the cars. And so we say that the net force is approximately 0 during the collision because the force of interaction between them is so much bigger than the force from the Earth. It's not equal to 0, but for calculational purposes, it's approximately 0. Second, the time of the collision. The actual time for the collision between two cars is very, very small. So you have a negligible force compared to the interaction force and a very small time. And so we say, to a good approximation, the momentum is going to be conserved regardless of the type of collision, but only during the collision, not before the collision, not after the collision, only during. My son's lunch is in my office, which is why I got this application. Okay, another quick question to end the day. In which case is kinetic energy conserved? Okay, Augusta. Okay, good enough. Okay, now this one I just explained. Jeffrey, give us your answer here and your reasoning. Okay, that's not correct. Right, I went over elastic means no loss in kinetic energy. And so the definition of elastic collision is kinetic energy is conserved. Okay, we're out of time. I know I did not get to any new material, but at least we got some reviewing. I'm going to do another problem here. Did you guys do this problem already? It's an example. Okay. I'll actually do the problem probably in lab, beginning of lab.